All right, so I'm going to explain the problem BOMAS. So in this problem, you're given a bunch of circles, and so some circles are query circles, some circles are fencing to keep animals in, so that's what BOMAS is. And what we're trying to do is we're trying to put animals in these containers so that no two animals only have a single fence between them. And so for this one, you can see on the right, I got 1, 2, 3, 4 different containers for the animals, and no two containers are contain the same animal, and so are animals next to each other. And so what we want to do is we want to query all these queries. So if we build a hypothetical BOMAS in the query circle, what I can do then is figure out where do I place the animals so I can maximize the number of animals that I place in the BOMAS. The problem is we have up to 10 to the 5th queries, or 10 to the 5th queries and circles that were given initially. So that's way too much to do naively. So one of the things we can do is think about the circle instead of as a single circle for each circle. We can think of it as two different curves, a lower curve and an upper curve. And that just makes it a lot easier for us to decompose these nested circles into a tree. So if you think about the largest circle could be the root of the tree, and then each layer down, if a circle is immediately inside some other circle, then it's a child of that node. And so what we want to do is we want to find this tree very quickly. So what we can do is if I drew a line from the start of the circle on the left side to up to infinity, the first circle that I hit gives me some information about where it is in relation to this tree. And so what we can do is we can shoot a line from a circle, and if we end up hitting the upper envelope or upper curve of the circle, then we know that that circle is including ours as a parent. But if we hit the lower bound of the circle, then we know it's a sibling. So in this case, this circle right here, it traces the upper bound and then goes up again. This is a sibling. So what we can do is we can form this tree where some of our edges we have sibling connections, and some of our edges we have parent connections. And so then the idea is once we have this sibling parent tree, we can then convert it into a regular binary search tree, just doing some very simple arithmetic on these pointers. So it's very similar to union find, but you can do it in O of n. So then the next step is, what we can do is we need to do a sweep line technique so that you can very efficiently find these upper and lower curves. So the idea with the sweep line technique is we're going to sweep from left to right, and we want to think about key points in that circle and maintain a data structure that has all the active circles that intersect that line at that time. So what we can do is we can think about the key points. The key X points for our sweep line is the start or the end. When we're at the start of a circle, what we can do is we can query what's the circle that's above us, what's the first curve that's above us, like we did here. But we can also insert the two curves into our data structure. And then when we get to the end of the curve, what we can do is we remove this from our data structure. And so we need a data structure to hold this, and a great data structure is a binary search tree. So if you're in Java, you can use tree set. If you're in C++, you can use multi-set. And then what we are going to sort by is sort by the y-coordinates of where we currently are in the curve as we're moving from left to right for a given x. So the key insight to this problem is that the circles don't intersect. So in other words, if we move this sweep line slightly to the right, you'll notice that even though the exact y value changes, the relative ordering of each of these curves as we go from top to bottom remains the same. So if we change our comparator for a new x coordinate to sort by y, it doesn't break this invariance of keeping this order. So what we can do is we can change the comparator on the fly. So depending on where we are at our x coordinate, our comparator is working on the y coordinate at that current time. And so doing this, we can do our sweep line. We can extract a rooted tree for all the circles. So then the second part of the problem becomes where do we place the animals in the BOMAS? We can think of it as a problem on a tree what's the maximum independent set that is on the tree? What's the maximum number of nodes I can select such that no two nodes are adjacent to each other? And so we can do this with dynamic programming. The state becomes which node we're currently at and whether or not we took the parent node, placed animals in the parent node. But there's one small detail is our tree structure also contains the query nodes, or these query circles. So we need to handle that specially. So we add them to our tree, but then if we ever come across a query node, we compute the answer for it normally, but then we also save some information that would propagate these two numbers as they would respond to the next query. So you propagate the information upward, and now every time you end up hitting a parent node, if it hits a query node, it just takes that aggregate information as it was a couple nodes lower than you in the DP. And so once you have all that together, what you can do is run this entire algorithm and get all the queries at once, and then spit them all out at once you've calculated them all together. And that's the solution to BOMAS.